Acid chlorides are named based on the carboxylic acid that would be used to make that acid derivative. As an example, acid halides, which includes acid chlorides and acid bromides, in order to name them, we had to convert the carboxylic acid name. In particular, we got to change the ic acid ending to a YL followed by the halide, chloride or bromide. As an example, here we have acetyl chloride. So this compound is named from the carboxylic acid that it came from. So that carboxylic acid would be acetic acid, which has this structure. It has a carboxylic acid and it has a methyl group here. So this compound, this carboxylic acid, if we replace the OH group with the chlorine, we have acetyl chloride. So we derive the name from the carboxylic acid, which is acetic acid. We change the ic acid ending to YL, right? So acetyl, and then add the halogen, which is chloride. So acetyl chloride would be the name for that compound. The next acid derivative here is benzoyl bromide. So we have changed benzoic acid into benzoyl bromide. This next example has 1, 2, 3, 4, and 5 carbons. It is an acid bromide, so this is named as pentanoyl bromide. If we had an OH here instead, it would be named as pentanoic acid. So we drop the ic acid ending, replace it with YL bromide. We also have a substituent on carbon 3, a hydroxy substituent. So that is added in front of the name, 3-hydroxypentanoyl bromide. And then lastly, the stereochemistry is S around carbon 3. So you can determine that by the fact that this oxygen has the highest priority around carbon 3. Then between carbon 4 and 2, we have 2 identical CH2 groups. The second carbon is bonded to another carbon, which has bonds to oxygen, bonds to bromine, while this one, carbon 4, is bonded to carbon 5, which has only hydrogen. So this is a higher priority group than carbon 4, which would be priority number 3. There's also a hydrogen facing back here, which has the lowest priority. So we could ignore that for now. So we go from 1 to 2 to 3. Notice we're going counterclockwise, so that is S stereochemistry. In the last example here on this slide, we have a compound that has an alkene. It has an acid chloride group. The carbon of the carbonyl is the highest priority carbon. So we start counting there. 1, 2. Then we go in this direction to include the double bond. So 3, 4, and 5. So this is a pentanoyl chloride, right? We have also a double bond, so it's actually pent 3-ene oil chloride. And then we have a substituent on carbon 2, which is an ethyl group, so 2-ethyl. And then lastly, we look for stereochemistry. The only stereochemistry here is this double bond. Notice carbon 4 has a methyl group that way. It also has a hydrogen this way. Between carbon 5 and this hydrogen, the carbon labeled as 5 has a higher priority than the hydrogen. And on this side, we have a hydrogen, and we also have the carbon that we labeled as 2, which has a higher priority than the hydrogen. So the carbon 2 and carbon 5, which is the 2 highest priority groups around this double bond, they're on opposite sides, so this is the E isomer of this alkene. Symmetrical anhydrides, for as far as naming, we're going to change the acid ending of the carboxylic acid that is used to make that anhydride with the suffix anhydride. So as an example, this symmetrical anhydride, if we split it in half and turn each side to a carboxylic acid, we actually have two molecules of propanoic acid hidden with this anhydride. So again, imagine splitting this anhydride down the middle and turning this carbonyl into a carboxylic acid, which would look something like this. And the same thing happens on the right side since it is a symmetrical anhydride. So notice if we ignore the oxygen in the middle, notice there are two molecules of propanoic acid hidden within this anhydride. And so we would name this compound as propanoic anhydride rather than propanoic acid. In the next example, again, if we split the anhydride down the middle and think of the left side and the right side as two different carboxylic acids, we would name those carboxylic acids as acetic acid. That's the common name for it. Or if you want to use the IUPAC name, it would be ethanoic acid. If we change the acid ending with anhydride, we have the name for this anhydride. So it's acetic anhydride. The next example, again, if we split this in half and turn each half into a carboxylic acid, we would have benzoic acid. So this anhydride is named as benzoic anhydride. For unsymmetrical anhydrides, we have essentially two carboxylic acids joined together to make the anhydride. So in order to name unsymmetrical anhydrides, we give the names of the two carboxylic acid compounds hidden within that anhydride, and we ignore the acid part. We replace that with anhydride. The two carboxylic acid names will be named in alphabetical order. So as an example, this compound here, if we split it in half, and again, if we imagine adding an OH group where this oxygen is attached, and we ignore this oxygen for now, and if we put another OH group here, the two carboxylic acids that would be used to make this anhydride, which we'll talk about later when we cover reactions, would be acetic acid from the left side and benzoic acid from the right side. So putting those in alphabetical order, this anhydride would be named as acetic benzoic anhydride. In naming esters, we're gonna give the alkyl group that is attached to the oxygen of the ester in front of the name, followed by the suffix ate, which is going to replace the suffix ic acid from the carboxylic acid. So as an example, we have here a compound that if we think about which carboxylic acid this came from, we would have to ignore this part and put an OH here. If we were going to name this carboxylic acid, we would name this as, since it has 3 carbons, so it has 1, 2, and 3. This would be named as propanoic acid when it's a carboxylic acid. It has a methyl group on carbon 2, so it would be named as 2-methyl propanoic acid if it was a carboxylic acid. When it is an ester, we change the ic acid ending with ate. We also have an ethyl group on the oxygen of the ester. That ethyl group goes in front of the entire name, so this entire compound is named as ethyl 2-methyl propanoate. The next example has an ester that, if you think about which carboxylic acid it came from, it would be benzoic acid. So again, ignore the alkoxy group on the ester for a moment. We would have this carboxylic acid. So the compound as an ester is named, instead of benzoic acid, is named as benzoate. So drop the ic acid ending of the carboxylic acid and replace it with 8, and you have the parent name for the ester. We also have an isopropyl group on the oxygen of the ester, so that goes in front. If there were any substituents, those substituents would go in between this isopropyl and benzoate. The next example has a terp-butyl group on the ester, so that goes in front, terp-butyl, followed by, we have 1, 2, 3, 4 carbons, so that is named as butanoate. This last simple example has an ethyl group on the oxygen of the ester, so it's named as ethyl, and then the rest of the molecule is named as acetate, since it comes from acetic acid. Naming amides is slightly more complicated than the other acid derivatives. The way we go about it is, at least for primary amides, we simply replace the ic acid or oic acid suffix for a carboxylic acid with the suffix amide for amides. So as an example, if we have 6 carbons in the amide in the parent chain, and we have a primary amine, we would name this as a hexanamide to indicate there are 6 carbons and it is an amide. In the next example, we have 5 carbons in the parent name, so this is named as a pentanamide. We also have an amino group on carbon 3, so 3 amino. And then notice carbon 3 has stereochemistry, which is R, and we can confirm that by the fact that we have an amino group, the nitrogen, which is the highest priority group directly attached to carbon 3. We have this carbon 2 and carbon 4, which are both CH2 groups. They're identical groups, so we want to move on to the next groups attached, which is carbon 1 and 5. Now, carbon 5, notice, has a carbonyl, while carbon 5 has only hydrogens. So that means that carbon 2 is the second priority group, and then carbon 4 is the third highest priority group around carbon 3. So if we go from 1 to 2 to 3, we're going to go in a clockwise fashion. So that means that the stereochemistry of carbon 3 is R. For secondary and tertiary amides, it gets a little bit more complicated. When it comes to secondary and tertiary amides, we have alkyl groups attached to the nitrogen of the amide. And we indicate those groups by the locant N, meaning the N, capital N, tells you that you have an alkyl group on the nitrogen of the amide. Now, if you have 2 of the same alkyl groups, we would use the prefix N, N to indicate that we have that particular repeating alkyl group on the nitrogen. We also have to replace the suffix of the carboxylic acid where this amide came from being ic acid or oic acid to amide. Here's a few examples actually. The first one has carbonyl of the amide plus another 4 carbons in the parent chain, so there are 5 carbons, and this is an amide, so it's named as pentanamide. We also have an ethyl group on the nitrogen, so that's added in front, and so we name this as N-ethyl pentanamide. With the next example, we have 2 methyl groups on the nitrogen, so those substituents are added to the name as N, N dimethyl, and then we have 7 carbons in the parent chain, so it's heptanamide. In the next example, we have 2 different alkyl groups, a propyl group and a methyl group. Just like any other substituent, we want to alphabetize these substituents. So methyl goes first. So N-methyl, N-propyl goes in front of the parent name. The parent name is derived from having 6 carbons, includes a double bond on carbon 3, and of course the amide. So this parent name would be hex to indicate there are 6 carbons, 3-ene to indicate there's a double bond on carbon 3, and then finally amide. Note that we don't need to say where the amide is located since it's assumed to be on carbon 1. We have also stereochemistry for the double bond, which is E. You can confirm that by the fact that carbon 2 is going in the opposite direction as carbon 5. So the two largest groups around the double bond between carbon 3 and 4 are opposite to each other, so that would be E stereochemistry. This next example illustrates how you would treat a compound, an amide, that has both substituents on the nitrogen as well as somewhere on the carbon chain of the parent name. So we basically treat the 3 different substituents the same way, other than we use the letter N to indicate the location of the groups on the nitrogen versus a number to indicate the location of a substituent on the parent chain. So we are going to alphabetize these groups the same way, whether they're on the nitrogen or they're not. So in this example, we have an ethyl group. So that goes before methyl. So as far as the substituent, we would name this as N-ethyl, and then N-3 dimethyl. So N and 3 say that we have a methyl and methyl on carbon 3 as well as on the nitrogen. And lastly, the parent name of this compound has 5 carbons, so this is named as a pentanamide. Last thing is we have an example here where we have a propyl group and an ethyl group. We also have a methyl group on carbon 3. So we indicate where the substituents are with the locant. The N-ethyl tells us we have a nitrogen with an ethyl group, a nitrogen on the amide with an ethyl group. We also have a methyl substituent on carbon 3. And then we have a propyl group on the nitrogen as well. So notice we alphabetize the 3 substituents, whether they are on the nitrogen or somewhere on the parent chain. It does not matter. We alphabetize them and treat them the same way. Lastly, we have 4 carbons in the parent name or the parent chain. So this is a butanamide. With this question, we're going to review one of the examples of naming acid derivatives. So we want to draw the structure of a 4-methyl pentanoyl chloride, which is an acid chloride. To draw this acid chloride, we want to sort of break this name down. We have a pentanoyl chloride, which means an acid chloride, which has 5 carbons. So carbon 1 on the carbonyl, carbon 2, the CH2, another CH2, another carbon, and then a CH3. So 5 carbons in the parent name. We have also a substituent on carbon 4, which is a methyl group. So the carbonyl is carbon 1, and counting down, this carbon here is carbon 4, which has a methyl group. So this is the structure that we're looking for.